All right, let's play detective for a few minutes. We're going to try and crack a case that's, believe it or not, hiding in plain sight. It's something you see pretty much every single day. Today, we are on the case of the blue sky.
You know, every good investigation starts with a question. And this one, well, it's about as universal as it gets. I guarantee that at some point, probably when you were a kid, you just looked up and asked yourself something incredibly simple, but also kind of profound. It's a moment of curiosity that basically connects all of us.
And that's it. That's the mystery. Why is the sky blue? It seems so basic, right? But the answer is actually this fantastic journey through the physics of light, the chemistry of our atmosphere, and even the biology of our own eyes. So let's start gathering the clues. Okay, to solve this, we've got to start with our main piece of evidence: sunlight. I mean, this stuff travels 93 million miles to get to us, and when it finally arrives, it's holding a major secret. So to our eyes, sunlight just looks white, or maybe a little yellow, just bright white light. But that whiteness, it's really an illusion. It's actually a mashup, a mixture of a whole bunch of different colors, all blended together.
And here they are. Sunlight is made of all the colors of the rainbow. Scientists call it the visible spectrum. And yeah, you know the drill. Red, orange, yellow, green, blue, indigo, and violet. Every single one of them is packed inside that one beam of what we see as white light.
Now here's where it gets really, really interesting. It's how these colors travel. See, each one moves through space as a wave. But, and this is absolutely crucial, they are not all created equal. Some waves are long and lazy, kind of stretched out, while others are super short and choppy. This difference is the key. So on one side, you've got your short wavelength light. Think blue and violet. These guys are high-energy, rapid little waves. Then, on the other side, you have the long wavelength, like red and orange. They're much more stretched out, lower in energy. You gotta remember this distinction. It's our clue number one. Okay, so we've got our light. We know it's a mix of different waves. Now, where does it go? Well, our next clue isn't way out in space. It's right here at home, in the air that's literally all around us. Our atmosphere, it looks totally invisible, right? But it's actually like a giant, dense sea of tiny, tiny particles. It's mostly made up of nitrogen and oxygen gas molecules. And these little guys, well, they're about to have a major run-in with all that incoming sunlight. Now, this interaction actually has a scientific name. It's called Rayleigh scattering. And it's basically what happens when light smacks into particles that are way, way smaller than the light's own wavelength. This single phenomenon is at the absolute heart of our case. So how does it work? It's actually pretty simple. A beam of sunlight comes flying in, it smacks right into a gas molecule, and that molecule absorbs the light for a split second and then shoots it back out, but in every possible direction, up, down, sideways, all around. It's like billions of tiny disco balls for light. All right, let's recap. Clue number one, light comes in different colors with different sized waves. Clue number two, our atmosphere is full of tiny particles that scatter that light. Now, it's time to put them together and solve this thing. And here it is, the crucial point, the big reveal. When those little gas molecules start scattering light around, they do not treat all the colors the same. Not at all. They totally play favorites. And this is the fundamental rule. Those shorter, high-energy wavelengths, that's our blue and violet light, they get scattered all over the place, far more easily and effectively by the air molecules. But the long, lazy red and orange waves, they tend to just muscle their way right on through with way less disruption. So because that blue light is getting ricocheted around like crazy, it essentially just fills the entire sky. It means that no matter where you look up, some of that scattered blue light is traveling from the atmosphere directly into your eyes. And that is why the sky looks blue. Case closed. Or is it? Hold on a second. If you've been paying really close attention, you might have a nagging question. You know, a good detective always looks for that one last twist, and trust me, there's a big one here. Exactly. According to the rule we just learned, violet light has an even shorter wavelength than blue light, so logically, it should scatter even more effectively. So why on earth don't we live under a big, beautiful, deep violet sky? Well, it turns out the answer comes in two parts, and it's just this fantastic combination of factors. The first part of the answer actually has to do with the source of the light in the first place, the sun.
So yeah, while the sun sends out all the colors, the mix isn't perfectly even. It just so happens that the sun radiates a little bit less violet light compared to the amount of blue light it sends out. So right from the start, there's simply less violet light available for our atmosphere to scatter.
But that's not the whole story. The second reason, and honestly it's maybe the more important one, has nothing to do with physics in the sky, and everything to do with the biology that's going on inside our own heads.
So check this out. First, there's a little less violet light coming from the sun to begin with. But here's the real kicker. Our eyes are just much more sensitive to blue light than they are to violet. This means that even with all that scattered violet light flying around up there, our eyes are just better built to pick up and register the blue.
And there you have it, the complete answer. The sky is blue because the short wavelength blue light gets scattered all across the atmosphere, and our eyes just happen to be perfectly tuned to see it. It's this amazing collaboration between the sun, the air, and us. It just goes to show you that even the most common, everyday things can hold some incredible secrets. The next time you look at a beautiful sunset or the deep green of a leaf, maybe ask yourself, is that color really what I think it is? What other colors in our world aren't quite what they seem?